A moon base looks shiny and heroic on day one, but what does it really look like after 100 years of vacuum, radiation, and human wear and tear? In this video, we're jumping deep into that century-long time-lapse to see how a real lunar city ages, breaks, mutates, and reshapes not just the moon, but the future of the entire solar system. Let's start with the most basic thing, the temperature swings. A lunar day from sunrise to sunrise is about 29.5 Earth days. That means roughly 14.5 days of sunlight, then 14.5 days of darkness. Over 100 Earth years, your base sits through around 1,200 of these light-dark cycles. In the daytime, exposed surfaces can heat up to about plus 127 degrees Celsius, around 260 degrees Fahrenheit. In the night, they can drop to about minus 173 Celsius, around minus 280 Fahrenheit. That's a swing of roughly 300 degrees Celsius every month. Metal beams, pressure hulls, cable trays, everything expands in the heat, then contracts in the cold again and again. On a single day-night cycle, the change is tiny, maybe a few micrometers across a panel, much smaller than a human hair. But metal and composite structures do not forget those cycles. They accumulate fatigue. Over years, microscopic flaws at welds and joints can grow. Adhesive bonds between layers in a composite can start to separate. Bolts and fasteners can loosen slightly, then work more each cycle. After a century, what looked perfectly rigid on day one has been flexed thousands of times, and the structure has a long history of stress built into it. So you might think, at least there is no oxygen, no water, so no rust, no classic corrosion, that should help, right? Here comes the twist. Vacuum solves one problem and creates another. In hard vacuum, materials that hold trapped gases, oils, or plasticizers slowly bleed those chemicals out. This is called outgassing. Take a rubber O-ring in an airlock, a plastic cable jacket, a drop of lubricant inside a bearing. Those all contain small, more volatile molecules that help keep them flexible or slippery. In vacuum, over years, those molecules evaporate away. In the short term, everything works fine. Over a decade, seals might get a little harder, glues a little more brittle, lubricants a bit thinner. After 30, 50, 100 years, if you never replace them, O-rings can shrink and crack. Cable insulation can split. Epoxy joints can lose strength. Spacecraft in Earth orbit already show these effects after just a few years. So a century on the moon with constant vacuum is a serious lifetime. So now you have structures cycling in temperature and materials drying and stiffening from the inside. But the moon is not just empty space passively surrounding you. It is sitting in a stream of high-speed debris. What happens when you add a steady rain of microscopic bullets? Micrometeoroids, tiny dust-sized fragments of rock and metal, hit the lunar surface all the time. They can be as small as grains of sand, often just milligrams of mass, but they move at insane speeds, roughly 10 to 70 kilometers per second, around 20,000 to 150,000 miles per hour. There is no atmosphere to burn them up, so they slam straight into whatever is exposed. Per square meter, the chances of a serious hit in any given year are low, but your base is not 1 square meter. A grown lunar settlement might expose thousands, even tens of thousands of square meters, considering solar panels, radiators, bunker roofs, vehicle garages, antenna farms. Over 100 years, it is statistically certain that some areas will be peppered with small impacts, and a few will take more significant hits. Each impact melts and vaporizes a bit of the local material, including the lunar soil, which then cools into little glassy beads and splashes. Surfaces become pitted and rough. Thermal control coatings get shredded. Solar panel covers get tiny craters that scatter light and cut efficiency. Outer walls pick up a permanent texture of scars. Over decades, the clean, bright, carefully tuned thermal blankets and coatings you started with turn darker, more irregular, less predictable. Now, add another constant stress that you cannot turn off, the space environment itself, the solar wind and radiation. No storms, but constant particle bombardment. How does that change the skin of your base over a century? The solar wind is a stream of charged particles, mostly protons and electrons, flowing out from the sun at hundreds of kilometers per second. On top of that, you have bursts from solar flares and coronal mass ejections, where particle flux and energy spike. Because the moon has almost no atmosphere and no global magnetic field, these particles can reach surfaces directly. When they hit, they can break chemical bonds in polymers, shift atoms in crystals, and slowly change the properties of paints, plastics, and even glass. High-energy ultraviolet light from the sun does a similar job. Over time, polyamide films, common in thermal blankets, darken and become more brittle. Coatings that were designed to reflect heat can lose their reflectivity. Glass faceplates on instruments or cameras can darken slightly, cutting the light getting through. We already see this in hardware left on the moon and in satellites. In a few decades, colours fade, materials crack, and performance drops. Over 100 years, if you do not replace or recoat them, many surface components are simply no longer doing what they were designed to do. The base turns into a catalogue of long-term material damage under vacuum and radiation. So now, stack everything together: thermal cycling, vacuum outgassing, micrometeoroid pitting, solar and particle radiation. If you tried to run a glass dome city entirely on the surface with thin walls and fancy windows, it would basically be a full-time emergency project. Constant patching, constant replacements, huge risk. This is why long-lived lunar bases end up looking very different from the early concept art. Engineers react in a very practical way. They bury almost everything. Even a layer of lunar soil 2 to 3 meters thick, about 6 to 10 feet over a habitat, gives huge benefits. It shields you from most micrometeoroids, it smooths out temperature swings, and it blocks a large part of the radiation from space. So the 100-year-old base is mostly underground, or at least under regolith mounds. Only what must see the sky is left exposed, like antennas, some radiators, docking structures, and carefully armoured airlock entries. Power cables are run in trenches, not on poles. Critical electronics are kept inside shielded vaults below the surface, connected by fibre optics to the hardware outside. In that setup, what really survives 100 years is not the visible surface gear. That stuff gets swapped out on a schedule. It is the buried pressure shells and tunnels, the deep infrastructure you designed it from day one for multi-decade life. The moon forces you into a bunker mindset, not because you are hiding from an enemy, but because empty space itself is the enemy. But even when you bury the base, you cannot escape one huge continuous stress: the pressure difference between Earth-like air inside and hard vacuum outside. That force is there every second, pushing out on every square meter of your habitat shell. Over 100 years, what does that do to the hull, the joints, and the supports that keep your air in and the vacuum out? Inside the habitat, you keep pressure at about 1 bar, roughly 100 kilopascals, similar to sea level on Earth. Outside, the pressure is basically zero. That means every square meter of the hull feels an outward push of about 100,000 newtons. That's like hanging a small truck off each square meter of wall and ceiling all the time. No break, no pause. The metal and composite structure is built to handle that, with big safety margins. But the key thing is, the stress never stops. On Earth, a bridge or a building sees loads that rise and fall, traffic comes and goes, wind changes. On the moon, the hull is sitting under that pressure difference 24 hours a day, year after year, decade after decade. Any tiny flaw in a weld, any microscopic defect in a joint, is living with that push constantly. At year 5, that flaw might be so small you can't see it, even with instruments. At year 30, it might have grown to a small crack. At year 80, in a worst case, it's big enough that it starts to change how the stress flows through that panel. You don't wait for it to pop, you have to detect it long before that. So you run structural health monitoring all the time. Strain gauges are bonded onto key beams and plates, measuring tiny changes in stretch. Acoustic sensors are bolted to the hull, listening for the faint sounds of crack growth, like clicks or pings, long before a human ear could notice anything. You log pressure fluctuations, you watch temperature gradients, You build up a detailed history of how each habitat ring or module has been loaded over tens of years. By year 100, that monitoring system is almost like a medical record for the base. It knows which sections are old but stable, which ones are showing early signs of fatigue, which ones need to be depressurized and retired. The habitat is not just a building anymore, it's a patient under permanent checkup, but that's only half the story. You're not just pushing outward on the hull with air, you're also pressing downward on it with moon rock. What happens when your radiation shield starts acting like a mountain sitting on your roof? If you bury the base, the regolith, the lunar soil, becomes part of the load path. Say you cover a habitat tunnel with 10 meters of compacted regolith, that's about 33 feet. That column of material over each square meter can mass on the order of 15,000 to 20,000 kilograms, around 3,000 to 4,000 pounds per square foot, depending on how dense you pack it. Even in lunar gravity, which is about 1/6 of Earth's, that is still a heavy load. The weight pushes down onto your support arches, into anchor bolts, into the interfaces where regolith shielding meets metal hull. Over time, the soil settles, grains rearrange, tiny voids close. That shifts where the stress goes. A support that was taking 20% of the load in year 5 might be taking 30 or 40% in year 50, because the ground around it compacted in a slightly uneven way. On Earth, civil engineers design bridges, tunnels and dams for 50 to 100-year lifetimes, but they have mountains of data from previous projects. On the Moon in the early decades, you do not have that. You are learning in real time how regolith behaves under long-term loading, under repeated thermal cycles, under moonquakes. So you design conservative, you overbuild, and you keep adding sensors into the ground and into the shells, into the supports, to see how reality compares to your models. The result is a kind of slow structural drift. Not catastrophic, but constant. Every few decades you go back to your design assumptions and adjust them. Newer tunnels might have different arch shapes, thicker interfaces, or different backfill patterns based on what the first generation taught you. So the walls and roof are under slow, continuous push and squeeze, but those are not the parts you push hard every day with your hands. The real daily punishment lands somewhere else. Where does the base actually flex the most in normal use? At the doors. Every time someone goes in or out, you cycle an airlock. That means you change pressure in that small chamber from near vacuum to habitat pressure and back again and again. You open and close hatches, you flex seals, you move valves, you swing hinges. On the ISS, hatch mechanisms and seals are checked often, and that's after only a few years of use. Now stretch that to decades. A main lunar airlock at a busy base might see thousands of cycles per year. Over a century, tens of thousands, maybe more. The gasket materials have to stay elastic from around minus 150 degrees Celsius to plus 60. That's about minus 240 to plus 140 Fahrenheit, depending on how exposed they are. They sit in vacuum when idle. They get blasted with UV and dust during EVAs. They get compressed and released over and over. By year 20, you've probably already replaced the first generation seals and even full door assemblies. By year 50, the original Mark I airlock design is long gone, replaced by more robust systems, better dust shields, smarter materials. By year 100, you're likely on airlock generation 4 or 5, with lessons from millions of cycles built into the design. You treat airlocks almost like aircraft engines, high cycle, high risk components with strict inspection intervals and hard life limits. If a hinge passes a certain wear measurement, it comes off. If leak rates creep above a tight threshold, that airlock goes out of service until it's rebuilt. You do not gamble on the doors because a failure there is a direct path from breathable air to vacuum. If doors are that sensitive, what about windows, the most fragile thing you can possibly cut into a pressure hull? Do big panoramic views survive 100 years, or do they quietly disappear? Transparent windows in vacuum plus radiation plus micro-impacts are a huge liability. Standard silicate glass darkens and becomes more brittle under radiation. Micrometeoroid hits can chip it. Thermal cycling can stress the layers. You can do better with exotic materials, like transparent aluminum oxynitride and multipane laminates, but nothing stays perfect forever. So the big curved glass dome that shows up in a lot of early artwork does not age well in reality. It is a maintenance nightmare, with high stress in the curves, huge temperature swings, and a big area for micrometeoroids to hit. Maybe you build one prototype in the early decades, mostly as a showpiece, but keeping it safe for 100 years is so expensive and risky that it probably gets depressurized, capped, or totally rebuilt into something else. What survives are smaller, thicker viewports. Narrow strips or round portholes, made from several layers of high-strength transparent material, each with its own pressure seal. These ports sit behind shutters most of the time, to protect from dust and radiation. They are swapped out on strict schedules, maybe every 10 or 20 years, long before they reach their theoretical failure point. Many of the original windows, if they still physically exist by year 100, are not in use anymore. They are covered over or preserved as museum pieces in low-pressure galleries, places you visit on tours to see how people used to look outside. The living working base depends more on cameras, augmented reality displays, and periscope-style optical systems instead of big open glass. But here's the key problem under all of this. How do you really know, deep down inside the structure, what a 50-year-old or 80-year-old module has gone through? Sensors tell you a lot, but not everything. At some point, you need to literally cut the thing open and look. How does that change the way you design the next generation? By year 100, you're doing autopsies on retired habitat modules. When a tunnel section or a living module reaches the end of its certified life, you don't just scrap it. You depressurize it, cut it apart in controlled conditions, and study it in detail. Engineers slice through 3D printed regolith walls to see how the internal microstructure held up under pressure and thermal cycling. They pull cross-sections of metal hull plates and look for crack growth, corrosion from the inside caused by humidity and trace chemicals in the air, or unexpected weaknesses near welds. They scrape off interior coatings and insulation to see how they aged, how much dust made it in, how microbes and human chemicals changed them. You compare all of that physical evidence with the sensor data and computer models you had while the module was alive. If your model said, "This area is low stress, but the real metal shows serious fatigue there," you adjust your design philosophy for the next generation. The moon base turns into a long-term lab for structural aging, not just for itself, but for every future outpost, on Mars, on icy moons, even in deep space stations. So by the time your lunar settlement hits 100 years, you are not just keeping people alive day to day, you are learning how to build habitats that might last centuries, maybe even 1,000 years, in places far harsher than the moon. But there is another silent threat that never stops during this whole century, and it doesn't just attack metal and glass, it attacks human cells and electronics from the inside. What happens to a base, and to the people inside it, when cosmic radiation has been hitting them for an entire human century? On the bare lunar surface, measurements from landers and orbiters point to an average radiation dose of about 1 to 1.5 millisieverts per day if you have no shielding. In more normal language, that's roughly 400 to 500 millisieverts per Earth year. For comparison, a chest CT scan is on the order of 5 to 10 millisieverts, so living unshielded on the moon would be like getting a strong medical scan every couple of weeks non-stop. Spread that over 10 years, you're in the range of several thousand millisieverts. Over 100 years, you're talking tens of thousands. At those levels, cancer risk isn't just higher, it's completely unacceptable. The dose is absolutely lethal long-term if you stayed that exposed. So by the time your base hits year 100, the only reason you still have a population is because you took radiation shielding as seriously as you take pressure and oxygen. So the obvious question is, how do you actually block this when you don't have an atmosphere or a magnetic field to help you? The main answer is simple and very heavy. You use the moon itself. Lunar regolith becomes your radiation armor. 2 meters of rock and dust, about 6.5 feet over a habitat, can cut the galactic cosmic ray dose by a big factor, roughly half or better depending on composition. Push that up to 5 to 10 meters, around 16 to 33 feet, and now you're getting dose rates that are closer to what airline crews get on long-haul flights near Earth, maybe even lower in some configurations. By year 100, dig and bury is standard practice, not some optional extra. Main habitats go in caverns or are tunneled into the subsurface. Surface modules you do build get berms of regolith piled up over them. Greenhouses that need light are either buried with light pipes and mirrors, or they sit in trenches with thick sidewalls and heavy covers for storm mode. Workshops, data centres, medical areas, all of it lives under deliberate shielding. You don't casually leave people working all day in thin-walled surface cabins. Unshielded time is strictly rationed, logged, and added to each person's lifetime radiation budget. If you can move a task into a shielded volume and run it by teleoperation or robotics, you do it. But even with regolith armour, you still have events that can spike your dose in hours instead of years. The slow drizzle of cosmic rays is one thing. What happens during a major solar flare that throws a huge burst of protons straight at you? Big solar particle events, the ones tied to strong flares and coronal mass ejections, can deliver hundreds or thousands of times the normal radiation level in a short window. Early in the lunar program, people treat these like weather storms. You get a warning from solar observatories, and everyone dives into whatever counts as a thickest wall room. After a century, that attitude hardens into infrastructure. The base has specific solar storm shelters, built like reinforced basements inside the already shielded underground network. These zones have extra layers of water tanks in the walls because hydrogen-rich material is particularly good at stopping protons. They use special plastics and composites chosen to slow and absorb high-energy particles. And on top of that, you still stack several meters of regolith. Every resident carries a dosimeter, sometimes integrated into clothing or implants. All those dosimeters feed into an AI-run monitoring system that tracks cumulative dose in real time. The system knows how much each person has taken this month, this year, and across their entire career. When a solar event hits, it can tell you exactly how long someone can safely stay in a less shielded zone before they must rotate out. Job assignments and shift patterns adjust to keep everyone under strict career limits. So hardware is shielded, shelters exist, exposure is tracked, but we still hit a big unknown, and this is where a 100-year base becomes a human experiment, whether you like it or not. What does lifetime radiation exposure plus 1/6 G actually do to human health across generations? Right now on Earth, and in low orbit, we only have data from astronauts spending months, maybe a year or so in microgravity with some shielding. We do not have hard numbers for people living decades in reduced gravity with chronic, slightly elevated radiation. The 100-year moon base is the first place where you actually see full life arcs under those conditions. By year 100, doctors on the moon and on Earth are looking at huge data sets, following groups of people who arrived as adults, people who grew up from childhood, and, eventually, people born on the moon. They track cancer rates across all organs. They watch for cataracts, which are sensitive to radiation. They study cardiovascular disease because radiation can damage blood vessels. They monitor fertility, pregnancy outcomes, and child development. You start to see patterns. Maybe certain cancers are noticeably more common, but only past a specific dose threshold. Maybe cataracts show up earlier than on Earth, so you standardize more frequent eye exams and better shielding for the head. In the best case, the data shows that with proper shielding and job planning, lifetime risk can be kept within what we accept for high-risk jobs on Earth, like nuclear workers or airline pilots. In the worst case, it forces a redesign of who can live there full-time and for how long. Either way, the moon base becomes the first multi-generation radiation epidemiology lab in reduced gravity. That data directly sets the rules for Mars, for rotating space habitats, for any long-term outpost beyond Earth. Radiation doesn't just hit people though, it also slowly attacks the electronics and power systems that keep the base alive. What does 100 years of high-energy particles do to your computers and solar farms? High-energy particles from cosmic rays and solar events can flip bits in digital memory, they can punch through transistor junctions in chips, and they can slowly damage the crystal structure in semiconductors. If you leave your critical computers on the surface with minimal shielding, you'll see random glitches, lockups, even permanent failures. So the 100-year base pushes all mission-critical electronics underground, behind thick regolith and sometimes extra local shielding. Surface antennas connect by fiber optic lines to buried communication hubs. Control systems run on radiation-hardened processors, often in triplicum. You use triple modular redundancy, 3 identical computers doing the same calculation, with a voting system, so if one gets a bit flip, the other 2 outvote it and flag the error. Solar panels also take a steady hit. Current tech in space tends to lose around 0.5% to 1% efficiency per year from radiation and micrometeoroid damage. That sounds small, but over 30 years that can mean losing a large part of your original output. Over 100 years, unless you replace panels on a rolling schedule, your power would collapse. So energy planning on a century-scale base includes continuous surface maintenance. Robots roam the solar fields, swapping out degraded panels, cleaning dust, checking for impact damage. Panels are treated more like consumables than permanent structures, with whole arrays designed to be dismantled and rebuilt over and over. Nuclear systems, buried and heavily shielded, pick up the slack during replacement cycles and during long nights or storms. Even structural materials feel radiation in slow motion. Plastics and composites can become brittle as bonds break. Some metals can see tiny changes in properties under long-term particle bombardment and neutron exposure near reactors. So material science doesn't stop once you build the base, it runs for the full century, constantly checking if your safety margins are still valid. Radiation is invisible, but with enough rock and planning, you can mostly push it under control. The threat you cannot bury so easily is the one you drag in yourself every time you open a hatch. The fine, sharp dust that wants to get into lungs, joints, and seals. So what happens to a moon base after 100 years of fighting not just vacuum and radiation, but a planet-wide layer of glassy dust that never goes away? Lunar regolith is not like beach sand, not rounded, not smooth. It's a mix of crushed rock and tiny glass fragments, mostly under 100 micrometers across, so smaller than the width of a human hair. These grains are created by constant impact events, rocks slamming into the surface at high speed, melting and shattering material. There is no air, no water, no wind or rain to slowly smooth those fragments, so they stay sharp, like broken glass ground down but never polished. During Apollo, after just a handful of spacewalks, suits came back with scratched visors, stiff joints, and worn fabric. That was from a few days of exposure. Scale that to 100 years of operations, thousands and thousands of surface trips, and you get a constant mechanical fight, dust cutting into seals, bearings, fabric, and coatings everywhere it reaches. The real problem is, dust doesn't stay politely outside. Every path that connects vacuum to a pressurized space is a way in. Airlocks, rover cabins, spacesuits, cargo containers, all of them can carry fine dust into the living areas if you are not extremely careful. Each EVA, each surface trip, might bring in only milligrams of dust stuck to boots, to tools, to suit joints. That sounds like nothing. But over a century, with thousands of EVA cycles, that adds up to kilograms of ultra-fine abrasive circulating in your systems. It settles in air filters, grinds inside hinges, sneaks into electrical connectors, and if you're unlucky, makes it into people's lungs. So the base has to treat air cleaning not as a small VAC problem, but as industrial-scale filtration. You run multi-stage filters similar to or better than HEPA systems on Earth, but tuned for even finer grains and sharper edges. You add electrostatic precipitators, plates or wires charged to pull in charged dust particles from the airflow. You use cyclone separators, spinning air so particles are flung outward and collected. The ductwork looks less like an office building and more like a factory that deals with toxic powder, because that's exactly what you're doing. And then there's the biology side, which is still one of the biggest unknowns over long timescales. What happens when those tiny glassy grains don't just scratch hardware, they end up in human lungs for decades? Experiments with lunar dust simulants on Earth suggest that very fine particles, especially under 10 micrometers, can travel deep into the lungs, into the smallest airways. Their surfaces can be chemically reactive, producing free radicals when they hit moist tissue. That combination of sharp edges and chemical activity can trigger inflammation, and over time that could lead to chronic problems, things like fibrosis, asthma-like symptoms, or even more serious lung disease. A 100-year base cannot treat dust as just a nuisance or a cleaning problem. It becomes a major occupational hazard like asbestos or coal dust was on Earth. Except here you know it from the start, and you have to engineer around it from day one. So you create strict dust zoning. There are clean interior zones where people live, sleep, and do most work, and these are protected aggressively. Outside that you have transition areas with decontamination gear. Closer to the surface or in mining and construction zones you have dirty areas where dust is expected, and people wear stronger protective equipment. Every worker who spends time in those black zones gets regular medical checks, lung function tests, imaging when needed, and their dust exposure is tracked across their career. To reduce dust entry at the source, engineers redesign how people even use suits and vehicles. Traditional suits, where you step into a suit that comes fully inside the habitat, bring dust in with them, so you move to suit ports. A suit port is mounted on the outside wall. The suit stays outside, you dock to its back, open a hatch and climb in from the inside. When you undock, the outside of the suit never enters the clean volume. Most of the dust stays outside too. After surface work, robots or exposed service bays clean and maintain the suits, not the people living areas. Rovers do not park in big pressurized garages filled with air from the base. They connect through their own ports, or stay in low-pressure bays where dust is expected and contained. Dirty wheels and undercarriages never roll across the residential floor. Inside, maintenance robots handle dusty equipment, so unprotected humans don't have to. Over decades, maintenance logs tell a clear story. Areas that mix dusty operations with clean functions are a nightmare. Constant repairs, clogged moving parts, air filters wearing out too fast. So by year 100, the layout of the base reflects that hard lesson. White zones and black zones are separate, with very few connections, and every connection is full of filters, vacuums, and cleaning gear. You still have one more lever to pull. You can try to stop dust from sticking in the first place. On the moon, dust grains charge up easily from ultraviolet light and from the plasma environment. That charge makes them cling to surfaces, which sounds bad, but it also gives you a handle to control them. Engineers start adding electrostatic tricks. Panels around critical equipment can be charged in ways that repel dust, like putting a same charge fence in front of a sensitive surface. Active dust fences along the edges of landing pads or around solar farms use oscillating electric fields to push charged dust particles upward and away, or corral them into collection zones. Vibrating plates shake dust off radiators or sensors and guide it toward traps. Magnetic systems come in too, because lunar soil holds iron-bearing grains. Magnetic sieves and conveyors can pull those iron-rich particles out of bulk regolith. That serves two purposes. You get useful raw material for industry, and you reduce the fraction of the nastiest dust around sensitive systems. Over time, the base may actively mine and process local soil, not just for metals and oxygen, but to condition the surrounding ground so it throws less problematic dust at you. By year 100, dust hasn't gone away. It never will. But it's not a purely random threat anymore. It's been pushed into a controlled role, a feedstock for industry in black zones, and something that almost never shows its full power inside white zones, if your systems are working right. You've turned part of the enemy into a resource, but only through constant, heavy engineering. Even with dust under partial control, you still have another slow, invisible process running the whole time. While the environment is chewing on your hardware, the moon's low gravity is quietly reshaping human bodies, from bones and muscles to hearts and maybe even brains. So after 100 years in 16G, what does a normal human body look like? And can that body still safely go home to Earth? On the ISS in almost 0G, astronauts can lose around 1 to 2% of bone mass per month if they don't train hard. That's crazy fast. The moon is better because gravity is about 1.62 meters per second squared, roughly 1/6 of Earth's, but it's still a lot less than what your skeleton evolved for. A 70-kilogram person on Earth weighs about 70 kilograms force. On the moon, that same body weighs only around 11 to 12 kilograms, roughly 25 pounds. Your bones and anti-gravity muscles, the ones that hold you up and fight Earth weight, now get much weaker mechanical signals by default. Over a few months, you mostly get away with it, especially with exercise. Over decades, especially for people who arrive young or who are born there, you start to see real structural changes. Skeletons tend to be lighter. Hip joints and spines can develop slightly different shapes, optimized for lower load. Leg muscles, calves and thighs don't need to bulk up as much. The whole body quietly shifts toward a low-load configuration. That sounds fine until you think about what happens if that person has to go back to Earth. A bone that is perfectly adequate in 1/6G can be borderline fragile at 1G. A simple fall on Earth could mean a serious fracture for someone who has lived decades on the moon, even if they never had a problem at home. And it's not just bones and muscles. Gravity also tells your fluids where to go. Change that, and your circulation system has to rewrite itself. On Earth, gravity pulls blood and other fluids toward your legs. Your body compensates with blood vessel tone and heart output. In low gravity, that head-to-foot gradient almost disappears. Astronauts in orbit get puffy faces, thin-air legs, and they often feel congested in the head at first. On the moon, the effect is less extreme than in 0G, but it's still there. Over years, your body adapts. Baseline blood pressure may shift. The heart doesn't need to pump as hard against gravity, so over long timescales it might remodel slightly, maybe a bit smaller or with different wall thickness. Blood volume can change, because your body decides it doesn't need as much fluid to keep everything supplied. For a permanent lunar resident, that becomes the new normal. They feel fine at 1/6G. The real test comes when they visit Earth or even a rotating habitat with higher artificial gravity. Suddenly their heart has to push harder. Their blood has to fight down toward their feet again. Some will handle it with a bit of training. Others may feel dizzy, faint, or even collapse. They may need compression suits and careful rehab just to tolerate standing upright at 1G for more than a short visit. By year 100, doctors have full lifetime records on thousands of people living in this in-between gravity. And they finally have hard numbers, not guesses, on what 1/6G really does to human circulation over 10, 20, 50 years. Then you hit the question that makes everyone nervous. What about children? What does it mean to grow from embryo to adult in low gravity? Right now, we have basically no human data on pregnancy, birth, and childhood development in reduced G. The early decades on the moon are probably very conservative. Pregnancies are rare, heavily monitored, and ethics boards argue over every step. But by year 100, you almost certainly have a first full generation of moon-born humans, people who have never lived under 1G. Doctors and researchers track everything: organ development, bone growth plates, the vestibular system in the inner ear, which tells you which way is up, motor skills, balance, coordination, neurodevelopment, because your brain is adapting to a different environment from the very start. You might discover that kids need regular time in higher gravity during certain growth phases. That could mean spinning gravity rooms at around 1G, where children spend a few hours a day running, playing, and stressing their bones and muscles like Earth kids, just to lock in normal development. There might be strict protocols, for example, in the 3rd trimester of pregnancy, or during early childhood, that require scheduled artificial gravity exposure. Your pediatrics department isn't just a clinic anymore, it's also a research lab. Every measurement feeds back into global policy, because whatever you learn about raising healthy children at 1/6G will shape how we think about families on Mars, on rotating stations, and in deep space. To push back against all these low-gravity changes, you don't just trust natural adaptation. You build an entire layer of technology and routine around forcing the body to remember 1G. Centrifuge gyms become standard. These are large rotating rings or arms where you can run or cycle while feeling close to Earth gravity or even higher. An hour a day at 1G while doing high-impact exercise like sprinting or jump training sends strong signals into bones and joints. Some people might train at 1.2 or 1.3G for extra margin. You also use exoskeletons or smart suits that add artificial weight during normal activities. A simple walk down a corridor in 1/6G can be turned into a serious workout if your suit is pulling you down with adjustable force. Vibration platforms load bones with rapid, small impacts, which are known to help maintain bone density. On top of that, medications tuned to bone metabolism become routine tools. Drugs that slow bone loss or stimulate bone formation may be used in cycles, especially before Earth visits or during key development windows for kids. Cardiovascular drugs help manage blood volume and pressure when someone transitions between different gravity levels. The target is clear and very practical. You want a lunar resident who can, if needed, get on a ship, spend a few days in transit, and step onto Earth without ending up in intensive care. Not everyone will qualify for that, but the system is built to make it possible for as many as possible. Even if you manage all that, the long game is still running quietly in the background. Over 100 years, and especially over multiple generations, something else starts to appear in the data. Slow, statistical drift in the human population itself. Genetic and epigenetic studies of moonborne residents show patterns. People whose bodies handle radiation better, who maintain bone density more easily at 1/6G, who tolerate closed, recycled atmospheres without weird immune responses, tend to have fewer health issues and often more successful pregnancies and kids. Over time, those traits become a little more common. We are not talking about a new species in 100 years, nothing that dramatic. But by then, if you put the graphs side by side, Earth populations and lunar populations are no longer identical curves. Average bone geometry might be slightly different. Certain gene variants related to DNA repair or bone metabolism might be more frequent. Typical resting heart function could differ. Culturally, you're still very much human. You watch the same shows, you talk to Earth every day. But physiologically, you're starting to drift toward a body that is tuned for 1/6G, shielded bunkers, and recycled air. The moon base stops being just a remote town and becomes a long baseline experiment on whether our species can really adapt to multiple gravity levels, or whether we lock ourselves into separate branches. And while all of that slow biological change is happening, there's another constant pressure on everyone up there, something that does not care about genetics at all. The whole time, for 100 years, you are living inside a closed ecosystem where every breath of air, every drop of water, and every bite of food has to be reclaimed, recycled, and kept stable. So what happens to a moon base when its life support system has been running almost closed for a full century, and a glitch isn't just inconvenient, it's life-threatening for thousands of people? On the ISS today, you already recycle roughly 90% of water and a big chunk of oxygen. For a 100-year lunar base with hundreds or thousands of people, that level is not enough. Shipping water from Earth forever is not an option. Near total closure becomes standard. You're aiming for 98 to 99% recycling of air and water every single year. Exhaled CO2 is not waste, it is feedstock. Solid oxide electrolysis units split CO2 into oxygen and carbon monoxide or solid carbon. Sabatier reactors combine CO2 with hydrogen to make methane and water. Bioreactors and plant beds pull in CO2 and release oxygen. All those loops are tied together, so if one line drops, others pick up the load. The scary part is, every kilogram of water that escapes to vacuum or gets locked inside a dead piece of hardware is gone for good unless you import more. So every leak is logged, every unexplained pressure drop is treated like a crime scene. Over decades, you map out all the failure modes, pipe fatigue, valve faults, human mistakes. By year 100, air and water systems are built from the accumulated statistics of thousands of small incidents that you never want to repeat. But keeping the air and water in the pipe is only half of it. You also have to keep everyone fed at scale every day, with almost nothing coming from Earth. How big does your farm have to be inside a rock to feed a city in vacuum? Take a base with 1,000 people. Each person needs roughly 2,000 to 2,500 kilocalories per day, depending on workload. Call it about 2 to 3 million kilocalories per day in total. You are not growing this in open fields. You are doing high-intensity farming, hydroponics or aeroponics, with artificial lighting or carefully managed sunlight. With advanced systems, you might get on the order of 30 to 60 kilograms of edible biomass per square meter per year, depending on the crop. That means you need tens of thousands of square meters of growing area, easily hundreds of thousands of square feet. You stack farms vertically, in racks, with LED panels tuned to plant absorption peaks. You run nutrient solutions in closed loops, reclaiming almost all water. In the early decades, you focus on raw yield, things like wheat, soy, potatoes, fast-growing leafy greens. But over a century, you learn that numbers on a spreadsheet are not enough. You have to tune crop portfolios for micronutrients, vitamins, and long-term mental health. People need variety, colour, texture, not just calories, so you start rotating fruits, herbs, spices, even small amounts of luxury crops, not for survival, but to stop people from burning out mentally on the same menu for decades. All of that plant and water hardware sits in a third layer of life support that is easy to ignore at first, but dominates in the long run. You're not just managing machines, you're managing microbiology. What happens when bacteria and fungi treat your base like a new ecosystem to colonize? Every closed habitat turns into a microbiome. Bacteria and fungi grow in air ducts, on damp surfaces, in water lines, in biofilters, in hydroponic tanks. Some are helpful, breaking down waste and supporting nutrient cycles. Others form biofilms that clog pipes, produce toxins or corrode metals. After a century, your life support team is not just engineers and plant scientists, it is also microbiologists with real power. You deliberately seed certain microbes into reactors and filters, species that you know are stable and helpful. You scrub out others with targeted disinfectants, UV light or phage therapy. You watch how these organisms mutate over time under radiation, disinfectant exposure, and low G-fluid dynamics. You maintain libraries of strains, frozen backups, and constant genetic sequencing of samples from around the base. If a new resistant biofilm starts spreading in a critical water loop, you spot the DNA signature early, you compare it to your library, and you hit it before it hits you. Once everything biological is in play, trash stops being a real category. Anything you throw away is lost mass, lost atoms that you could have reused. In a 100-year base, that is not acceptable. So what do you do with all the solid waste, human and industrial, that piles up in any normal city? You run it through another layer of loops. Organic waste, food scraps, human waste, plant clippings, all go into anaerobic digesters. These tanks use microbes to break material down into methane, CO2, and nutrient-rich sludges. Methane can feed fuel cells or chemical plants. CO2 cycles back to plants. The remaining solids can be processed into soil-like substrates or further broken down. Plastics are chemically recycled. You depolymerize them into base molecules and build them back into new materials. Metals are melted or chemically stripped and recast. Even waste heat gets captured. Warm air and water from people, lights, and machines flow through heat exchangers to preheat greenhouses or incoming air to cold modules. By year 100, the rule is harsh and simple. If something leaves the habitat as a trash bag, instead of going into a loop, someone in design or operations has messed up. You rate projects by how close they come to zero waste, not just for environmental reasons, but because importing replacement atoms from 400,000 kilometers away is expensive and risky. All of this adds up to one big truth. Your life support is not a static machine. It is a managed artificial ecosystem, and sometimes that ecosystem misbehaves. What does long-term stability actually look like when your environment is a set of tanks, lights, pipes, and genomes? all packed into a few cubic kilometers under the moon. Over a century, the base sees ecological incidents. Maybe an algae strain in an oxygen bioreactor suddenly blooms out of control, blocking light and crashing oxygen output. Maybe a plant pathogen wipes out a primary food crop in one module. Maybe a harmless skin bacterium evolves into a problem organism in your water systems. Each of these events forces change. You add redundancy by splitting life support into multiple modular biomes, semi-independent volumes with their own plant mixes, microbe communities and hardware. If one module goes bad, you can isolate it, treat it, and the rest of the base keeps breathing and eating. You diversify crops so no single disease can take out more than a fraction of your food. You pair biological systems with hard chemical backups. If a plant-based CO2 scrubber has to be shut down, stored chemical sorbents and electrochemical scrubbers can carry the load for weeks or months, at higher energy cost but with high reliability. By year 100, the base's life support looks less like a single closed loop and more like a layered safety net of overlapping loops, biological on top of chemical on top of physical. You are tending a domesticated biosphere inside metal and rock, and the survival of thousands of people depends on keeping that biosphere inside tight limits. But all of this complexity, air loops, water loops, farms, reactors, pumps, filters, sensors, only works if one thing never really fails for long: the energy supply. On the moon, that energy problem has a brutal twist: 2 weeks of day and 2 weeks of night. So how does a 100-year moon base keep the lights, pumps and heaters running through hundreds of 14-day lunar nights when one serious blackout is not an inconvenience? It's a mass casualty event. A lunar day from sunrise to sunrise is about 29.5 Earth days. Roughly 14.75 of those are daylight, 14.75 are darkness. If you tried to run purely on solar with no backup, every cycle your base would have to survive about 2 full Earth weeks with the sun gone. Now say your mature base draws tens of megawatts, 10 to 30 megawatts is a reasonable range for a small town-scale installation with life support, industry, farms and transport. Multiply that by 350 hours of night, and you are talking gigawatt hours of energy you need to store for each darkness period. Stretch that over 100 years, hundreds of these cycles, and you are into terawatt hours passed through your storage systems. On Earth, building storage that big would already be a national-scale project. On the moon, you need that level of reliability just to not freeze or suffocate. A simple solar plus battery setup is nowhere near enough. You need location tricks, multiple generation types, and layers of storage on top. So the first move is geographic. You cheat the day-night cycle as much as the moon allows. Where do you go? At the lunar poles, certain high ridges near crater rims catch sunlight for most of the month, up to around 80 to 90% of the time. These are often called peaks of near-eternal light. A 100-year base aims its main power infrastructure at or near those spots. You string solar farms along kilometers of high ground. In vacuum and with no weather, you can build very light structures, just frames and panels, no need to worry about wind or rain. The sunlight hitting the top of the moon is roughly 1,360 watts per square meter. With panel efficiency and angles, you only convert a fraction of that into electricity, but it's still a reliable, predictable number. You scale up thousands, then tens of thousands, then hundreds of thousands of square meters of panels. That gets you into the hundreds of megawatts or even gigawatt range if you really commit. From there, you route power down to the buried base by cables and high voltage lines. But these panels are not eternal. Dust slowly settles on them. Micrometeoroids pit their surfaces. Radiation degrades their cells. So constant robotic maintenance and replacement is built into the plan from the start. Small rovers brush and electrostatically clean panel faces. Larger service robots swap out entire modules and haul them to repair lines. The power system doesn't just generate electricity, it also supports a permanent panel factory that keeps the array healthy. Even with perfect placement though, you still get shadow periods and you still have eclipses and bad angles. You need something that doesn't care about sunlight at all. That means nuclear. To survive long nights and to ride through emergencies, the base leans on a nuclear backbone. In the earlier decades, that probably means fission reactors in the 1 to 10 megawatt range each. Later, if fusion becomes real, you bolt modular fusion units into the same role, but you don't bet the base on a technology that doesn't exist yet. These reactors are not sitting open on the surface. They are buried in dedicated tunnels, with thick regolith shielding on all sides. Heat from the core runs out to long radiative fins on or just below the surface, panels or pipes that glow in infrared and dump waste heat into space. Over a century, you go through several generations of reactors. Early units are run, then slowly powered down, cooled and entombed in place as radioactive waste. Newer, more efficient ones come online in new caverns. The nuclear waste chain is designed to be airtight with multiple containment layers, because a serious release into a closed ecosystem would be a disaster, not just environmentally. Even with solar and nuclear, you still have big swings, and you still need something to buffer the grid, to cover peaks and handle the long, slow drain of night. How do you store energy at that scale without building a battery the size of a mountain? You stack solutions. Batteries are still there, but they handle fast changes, seconds to hours, not whole weeks. High-density batteries, maybe metal air or solid-state systems, smooth out the noise, keep local microgrids stable, and give you a safety margin for quick faults. For 14-day nights, you add chemical storage. During the long daylight, you run electrolyzers that split water into hydrogen and oxygen. You store those gases in high-pressure tanks or underground caverns. At night, fuel cells recombine hydrogen and oxygen to generate electricity and water again. That's a clean loop, and the same gases are also useful for rockets and industry. Some designs also use gravity batteries. Picture massive carts or blocks, each loaded with tons of regolith, hauled up slopes or vertical shafts by electric motors when power is plentiful. During night or during a shortfall, you let those loads descend under control, turning motors into generators and feeding power back into the grid. In 1/6 G, you need more mass or more height than on Earth to store the same energy, but with deep shafts and heavy loads, you can still reach gigajoule scale storage. No single method solves the whole problem. The actual century-old grid is a hybrid solar and nuclear feeding into chemical storage, gravity systems and batteries, all linked by smart control software. The system doesn't aim for elegance, it aims for never-drop life support. And that's where the tension really sits. On Earth, a blackout might ruin the food in your fridge and shut down traffic lights. On the Moon, a full power loss is a direct threat to everyone. Habitat temperature starts dropping, pumps that move air and water shut off, CO2 scrubbers stop pulling carbon dioxide down, pressure control systems go idle. In a buried base, you have some thermal inertia, walls and floors that hold heat for a while, but if power does not come back in hours, you're on a clock. Early in the history of the base, there are near misses. Maybe a solar storm takes down part of the grid. Maybe a software bug misroutes power and trips reactors offline. Those events become turning points. After that, planners overbuild redundancy as policy. You get triple networked power buses, 3 independent main lines with automatic cutouts. Each habitat cluster has its own microgrid that can isolate in milliseconds and run on local storage and small backup generators. Deep in the complex, you install emergency chemical generators, sized not to keep everything comfortable, but to keep people alive, running only core heating, minimal lighting, and life support pumps for days or weeks with no main grid at all. Every watt is measured and tagged. You know which loads are critical, which are important, and which are optional. In a crisis, the system can shed non-essential loads automatically, shutting down heavy industry, non-critical labs, even some farm lighting sequences, to keep air moving and temperature stable. Engineers constantly run simulations of worst-case failures, chain reactions of faults, unlikely combos of events. They test the grid like cybersecurity experts test networks. They assume that if something can fail in a way that kills people, it eventually will, unless they redesign it. By year 100, the power system of the moon base looks more like the nervous system of a large animal than a simple power plant. It is everywhere, it has reflexes, it has redundancies, and it has one more job beyond just survival. It has to feed the huge appetite of industry. Because once you have stable megawatts, once you can ride through long nights without blinking, you stop just surviving. You start melting rock, stripping oxygen, and building a city out of the moon itself. So what happens when that same base, hardened against darkness and blackouts, starts pulling in millions of tons of regolith and turning it into air, metal, and fuel for the rest of the solar system? Start with what that grey stuff actually is. Typical lunar regolith is roughly 40 to 45% oxygen by mass, locked up in silicates and metal oxides. The rest is mostly silicon, iron, aluminum, magnesium, titanium, plus a long list of trace elements. At the poles, in permanently shadowed craters that stay below about minus 150 degrees Celsius, you also have water ice, probably in the billions of tons spread across many sites. By year 100, your base is not just sampling this, it is mining it at the scale of a mid-sized operation on Earth. Bucket wheel excavators chew continuous trenches in the regolith. Autonomous trucks or conveyor systems haul thousands of tons per day back to processing plants. Drills bite into icy soils in shadowed craters, sending crushed, frozen material up to heated processing hubs on the rims. Measured over a year, you're moving millions of tons of material, not as a one-time project, but as a steady flow. The moon is now your ore body, and the city lives off that ore. The key prize is oxygen. 1 ton of typical regolith can yield hundreds of kilograms of oxygen once you break the chemical bonds. That oxygen is life support, breathing air, and it is also oxidizer for rockets and industrial burners. There are a few main extraction methods. One is molten regolith electrolysis, where you heat regolith until it melts, then run an electric current through it. Oxygen ions migrate and form O2 gas at an electrode, and metals pull separately. Another is hydrogen reduction of ilmenite, a titanium iron oxide that's common in some lunar soils. You pass hydrogen gas over hot ilmenite, it grabs oxygen and turns into water, then you split the water and recycle the hydrogen. Over decades, you refine and combine these methods. The result is that by year 100, big parts of your O2 supply no longer come from shipped tanks or from water split just for air. They come straight from rock. The leftover mix of metals, iron-rich and titanium-rich alloys, aluminum and silicon compounds does not go to waste. It becomes raw material for construction and manufacturing. Here is where the base stops thinking like a camp and starts thinking like a factory. Instead of shipping steel beams and concrete from Earth, you build what you need with 3D printing and sintering of local material. Early experiments showed that you can use focused sunlight or microwaves to fuse regolith into solid bricks or slabs. After 100 years, that concept has gone fully industrial. Large-scale printers crawl along tracks, laying down continuous walls, arches, and vaults at speeds of meters per hour. They feed on pre-processed regolith powders, sometimes blended with binders or metal fibers made on site. You print radiation berms over habitats. You print long hangars for vehicles, thick-walled shielded tunnels and buried tank farms. You print roadways that do not kick dust everywhere every time a rover or train passes. For high-strength parts, you feed your extracted metal powders into metal 3D printers that can produce beams, trusses, pipes, pressure vessels and mechanical parts, all with minimal human handling. The point is simple: you do not ship concrete bricks or standard metal sections from Earth unless there is no other choice. You bake the moon itself into megastructures, including foundations for something even more dramatic: mass driver tracks that will fling cargo off the moon with no chemical fuel at all, but raw rock and metal are only half the story. The fuel that moves ships and the volatiles that chemistry depends on come from a different kind of mining in the dark. In polar craters, where sunlight never hits, you strip mine ice-bearing regolith. You haul it to processing modules where it is heated, releasing water vapor. That water is purified and split into hydrogen and oxygen. The oxygen goes 3 ways: into air, into oxidizer tanks for rockets, and into high-temperature industrial processes that need pure O2. The hydrogen pairs with oxygen as high-performance propellant. Liquid hydrogen and liquid oxygen, the same basic combo used in many heavy-lift rockets. Storage depots hold these cryogenic fluids in buried tanks. Some depots sit on the surface near launch sites. Others sit in low lunar orbit or at Earth-Moon Lagrange points, stable positions where it is cheap in energy to park mass. Tanker landers and tugs shuttle back and forth, topping up vehicles headed to high Earth orbits, to Mars, or to asteroids. By year 100, a significant share of all propellant burned in cislunar space is not coming from Earth at all. It is coming from those dark craters, processed and shipped by your lunar industry. The Moon has become a gas station and chemical warehouse in space. At that point, the economics flip. In the early decades, almost everything arrives from Earth, and very little leaves the Moon. The base is a cost centre. But over a century, you pass a tipping point, where more mass starts leaving the Moon than arriving. Outbound, you have oxygen, metals, structural components, refined propellants, and eventually high-value manufactured products. Large telescope mirrors cast and polished in low gravity, radiation-hardened components built and tested right under a cosmic ray bath, bulk structural rings and trusses that are too big and too awkward to launch from Earth easily. Inbound, you still get specialized items, high-precision instruments, some electronic, maybe luxury goods, but the core bulk is reversed. The Moon is now feeding the rest of the cislunar economy. When planners design missions to Mars or big space telescopes, they assume the heavy stuff, fuel, big metal structures, shielding, comes from lunar factories, not from Earth's gravity well. At that point, your 100-year-old base is no longer an outpost burning money. It is infrastructure. Its existence changes how every serious mission in the inner solar system is designed. Because now you can launch dry from Earth, light with no fuel, fly to lunar orbit, and tank up there. The cost curve for deep space shifts, but there's a catch. The more material you move, the more fuel you make, the more traffic you create into and out of that shallow gravity well. Rockets are landing and lifting constantly. Cargo is flying off mass drivers and vehicles are crisscrossing the surface. So how do you land, launch and move all that mass safely for 100 years straight on a world where rocket exhaust can turn loose dust into a sandblasting storm that tears your base apart? Rocket plumes in vacuum are brutal. There is no air to slow them down, so exhaust hits the ground at very high speed, then throws regolith out at tens of thousands of kilometers per hour. That's many thousands of miles per hour. Apollo already showed this. You can see the scouring and dust sheets in the footage from the 1960s and 70s, and that was from a tiny number of landings. Now scale that to a busy industrial moon. Hundreds, then thousands of landings and takeoffs over a century. If you let vehicles touch down anywhere near habitats or solar farms, that high-speed dust will sandblast panels, windows and radiators, and eventually dig craters under your own infrastructure. So by year 100, landing is fully separated from living. You have formal landing pads made of fused regolith or cast basalt, solid sheets of rock created by melting the top layer with microwaves or concentrated sunlight. These pads sit kilometers away from the main habitats, with clear approach corridors. Robots constantly clean those corridors. They brush, scrape, and maybe use electrostatic fields to pull dust off the pad surfaces and keep the area smooth and predictable. Cables, pipes, and structures are buried or shielded. Landers follow precise approach paths, so their exhaust and any remaining kicked-up dust are directed away from everything important. That solves where you land, but what about the vehicles themselves? How do you move cargo and people between orbit and surface for 100 years without throwing away ships every trip? Because the Moon's escape velocity is only about 2.38 kilometers per second, much lower than Earth's 11.2, you can realistically build single-stage reusable landers. These are vehicles that launch from the surface, reach lunar orbit, then come back and land again without dropping tanks or stages. They run on lunar-made propellant, liquid oxygen, and liquid hydrogen from local water and regolith. They come down onto those hardened pads, refuel, load cargo or passengers, then go back up. Over a century, you don't fly random prototypes. You develop families of landers, just like airliner families evolved from early biplanes on Earth. You end up with lunar buses and lunar freighters, standardized hulls and engines, with known maintenance routines and service lifetimes. Navigation and guidance are so precise that landing accuracy is measured in centimeters, even sub-millimeter alignment when docking with surface umbilicals. That precision matters, because a meter off target could mean blasting a trench next to a fuel line or a sensor mast. Between those pads and the buried city, though, you still have to move a lot of mass across the surface. Simple rovers can't carry an industrial economy on their backs. What does the ground transport network look like after 100 years? For small teams and flexible work, you still use pressurized rovers, the moon equivalent of trucks and vans. But for the real heavy lifting, bulk ore, refined metals, propellant, you go to rail. Maglev trains in vacuum tunnels or armoured trenches carry cargo at hundreds of kilometers per hour, hundreds of miles per hour. With no air drag, trains can be very efficient once they are up to speed. Tracks run from mining zones to processing plants, from those plants to mass drivers and landing zones, all without throwing dust into the sky. For medium-distance, fast cargo, you also use hoppers. These are vehicles that fire a short burst of thrust or get a push from an electromagnetic launcher, arc across the surface on a ballistic path, then land again. With no atmosphere, their trajectory is pure physics, no drag, just gravity and initial push. That lets you bounce material from ridge to ridge, crater to crater, quickly and cheaply as long as guidance is reliable. When you zoom out further, you hit the real game changer for bulk export. You stop using rockets for heavy cargo, leaving the moon at all. How do you throw mass off the surface using only electricity and rails? You build mass drivers. These are long linear accelerators, tracks that can run tens of kilometers, accelerating payloads with electromagnetic forces instead of burning fuel. To put cargo into low lunar orbit, you need to push it to a few kilometers per second. Around 2.5 to 3 kilometers per second is a typical target range. For a 10-ton payload, the kinetic energy at that speed is huge, comparable to the explosive energy of hundreds of kilograms of TNT. But it's not an uncontrolled explosion. It's delivered smoothly over the length of the track, powered by solar or nuclear electricity, controlled by switching systems. Payloads ride in hardened shells or on sleds that stay on the track, then release the cargo at the end. Some designs spin the cargo to average out forces, some use shock absorbers for the launch. The cargo might be raw metal ingots, tanks full of propellant, or sealed canisters of regolith headed to orbital factories. By year 100, the base likely runs one or more of these mass drivers, aimed along safe corridors where misfires won't send debris toward habitats or satellites. They feed depots in lunar orbit, which then redistribute material around cislunar space. The cost in fuel to move bulk goods from the moon has dropped close to zero, replaced by infrastructure and electricity. With all this machinery, it's easy to forget the people. How do humans actually travel in this system, when the moon has gone from a heroic destination to a regular but harsh stop on a wider route? The basic physics of the trip from the moon to low Earth orbit have not changed. With chemical propulsion, you are still looking at roughly 3 to 5 days each way, depending on trajectory. But by year 100, that journey is no longer an experiment, it is routine service. Radiation-shielded cislunar ferries run regular routes. These are larger transport vehicles that stay mostly in space, shuttling between Earth orbits, lunar orbits, and key waypoints like Lagrange points. They carry tens to hundreds of passengers and many tons of cargo in one go. You board from orbiting hubs, not straight from the surface. Lunar landers take you from the ground up to a station. From there, you transfer to a ferry with similar gravity and life support, so the transition is smooth. Interiors are designed for long, boring trips, not emergency missions, with medical bays, exercise areas, and radiation shelters built in. Flight windows and traffic lanes become a known pattern, just like airline routes. You can look up a schedule, book a passage, and know that in a certain number of days you will step off in orbit around Earth, then ride a re-entry vehicle down. The Moon at this stage is a rough, isolated mining and industrial town about 400,000 kilometers away, around 250,000 miles, or about 30 Earth diameters. But the highway there, the mix of landers, trains, hoppers, and ferries, is increasingly well paved. Once those transport lines are stable, something interesting happens. People stop thinking only about survival and cargo, and they start thinking about what they can learn when they can put sensors, telescopes, and labs almost anywhere on the Moon and keep them running for decades. So after you've built the roads and launch rails, what does a century of continuous science on the Moon do to our picture of the universe? Start with the far side of the Moon. That hemisphere never faces Earth, so it's permanently shielded from almost all of our radio noise. No FM stations, no cell towers, no radar, nothing. For radio astronomy, that's priceless. A century-old base takes full advantage of this. It builds radio arrays spread over tens of kilometers linked by buried fiber. Simple dipole antennas on the surface may be stations anchored into regolith, all listening at very low frequencies that are basically impossible to observe from Earth because our ionosphere blocks them. Those frequencies let you probe the cosmic dark ages, the time after the Big Bang but before the first stars and galaxies lit up. You map the faint glow from neutral hydrogen across billions of light years. You track how that signal changes with time and location, which sharpens the timeline of when the first stars formed, when they started ionizing the universe, and how structure grew. You're not just filling a gap in a chart, you are finally seeing a whole era of the universe that was invisible from the ground. Radio's one piece. The Moon also gives you something precious for other kinds of physics: stability. No atmosphere, low seismic noise, slow temperature changes underground. That makes it a fantastic place for ultra-precise long baseline instruments. Over 100 years, you anchor mirrors, gyroscopes, and timing stations across hundreds of kilometers. Some are used for interferometry, combining light or radio waves from distant objects with extreme precision. Others contribute to gravitational wave detection, acting as quiet reference points. You might link these lunar instruments with Earth-based detectors, effectively turning the Earth-Moon system into a single giant interferometer tens or even hundreds of thousands of kilometers across. You also put neutrino detectors in deep lunar caverns, shielded from background noise. With careful design, you can watch high-energy neutrinos from the Sun, from supernovae, and from distant galaxies, with less interference than you'd get on Earth. That data feeds right back into models of stellar cores, black hole mergers, and high-energy cosmic events. While those instruments stare outward, geologists use the base to stare inward at our own solar system's past. With permanent access, you don't just grab a few rocks near one landing site. You launch decade-long programs to systematically sample every major terrain, from ancient highlands to young lava flows, from polar regions to big impact basins. You bring back cores that go deep, not just surface dust. In labs under the base, you run precise radiometric dating on these samples. That pins down the ages of key impact events and volcanic episodes on the Moon with far better resolution than before. Because we use crater counts to estimate ages on other airless bodies, like Mars, Mercury, and many moons, improving the lunar timeline changes those estimates too. When you adjust the curve for how many craters per square kilometer equals how many billion years. Entire chapters of planetary history get new dates. You might find that certain heavy bombardment phases were shorter or longer than we thought, or that internal activity on some worlds lasted far longer. Textbooks on solar system evolution are rewritten with those numbers. The Moon is also a perfect testbed for high-precision physics in a controlled but extreme environment. You can build labs underground with very stable temperatures, tiny vibrations, and ultra-high vacuum on tap. In those labs, you put atomic clocks that are orders of magnitude more stable than current standards. You compare their tick rates at slightly different heights in 1/6 G to test general relativity over long durations. You set up quantum experiments, entangled particle systems that run for months or years to probe decoherence in a quiet setting. You run dark matter searches using low-temperature detectors and shielded volumes, taking advantage of low background radiation and mechanical noise. Some of these experiments give nothing found results, but at sensitivities Earth labs can't reach. Those null results are still huge. They rule out big chunks of parameter space for dark matter models, or for certain modifications of gravity, forcing theorists to adjust or drop ideas that look fine on paper. By year 100, the Moon is not just a place with telescopes. It's wired into a wider network. Data from lunar arrays and labs feeds into missions placed at the Earth, Moon, Lagrange points and beyond. Lunar industry now has the ability to make and launch very large, precise structures. So kilometre-scale space telescopes and interferometers, too big or delicate to launch from Earth in one piece, are built from lunar-made components in cislunar space. Robots assemble mirrors, trusses, and sunshades using parts cast or printed on the Moon and sent up via mass driver. Those space instruments, combined with lunar and Earth-based observatories, attack the biggest cosmology questions. Dark matter distribution, dark energy's behaviour over time, the fine structure of the cosmic microwave background, constraints on inflation in the early universe. Each big mission is supported by the infrastructure your 100-year base provides, from materials to propellant to data relay. The result is that our model of the universe, which was already radically improved by 20th and 21st century satellites, gets another full upgrade. Some theories survive, others are cut down by better data. Entire classes of models for how the universe expands, what dark matter might be, and how structure forms are confirmed or wiped out thanks to experiments that only make sense when a permanent moon base exists. All of that is the science wins side. But while your instruments are quietly listening to hydrogen from the Dark Ages and to distant black hole mergers, something else is evolving under that regolith shield. A city is growing, people are being born, growing up, growing old, and sometimes dying without ever seeing an open sky. The science rewrites the universe, but the society underneath it is slowly rewriting what it means to be human. So after 100 years of continuous presence, what does life actually look like inside that buried moon city, day to day, for the people who now call it home instead of Earth? Early on, you only have a few dozen people on rotation, maybe 100 at most, all highly trained, all temporary, but over a century that shifts. Industry, science and logistics need continuity. Short tours are expensive and disruptive, so the number creeps up into the hundreds, then low thousands of long-term residents. Birth start as rare cases, almost controversial. Medical teams treat the first pregnancies like high-risk experiments with strict oversight and backup plans. But once you get through the first few healthy births, you understand more about pregnancy in 1/6 G and under slightly elevated radiation. It stops being a one-off event and becomes a planned part of life. By year 100, age pyramids look weird compared to Earth. At the beginning, it's almost all working-age adults, very few children, almost no elderly. A few decades later, you see a bulge of kids and teenagers, all lunar-born. Later still, there's a second bulge, they're kids. Elderly populations are still smaller than on Earth, partly because many older workers retire back to Earth, and partly because long-term health outcomes in low G are still catching up. Life expectancy curves are no longer guesses based on astronaut data. You have real numbers. You know at what age certain radiation-related diseases become more common. You know how bone and joint problems track across decades. You know how many people make it to 70, 80, 90 in 1/6 G, and how many of them can safely travel to 1G again. Policy, insurance and medical planning are based on those numbers, not on optimistic promises. While that population adjusts physically, their day-to-day culture is shaping around a completely different environment. What does it do to people when outside doesn't mean fresh air? It means vacuum. There is no weather, no rain, no wind, no clouds, no oceans, no forests, no naturally open spaces. The only trees you ever see are in controlled biomes, greenhouse parks under lights. Sunlight is something you schedule exposure to, not something that just appears, so culture pivots around different anchors. Holidays are not tied to seasons in the same way, because seasons are mostly meaningless underground at the poles. Instead, people celebrate safe arrivals of major cargo convoys, activation of a new reactor, the commissioning of a new tunnel, the anniversary of first landing, or the successful repair of a major failure. A good harvest cycle in the farms is a big event. A year without a major safety incident is worth celebrating. Over decades, speech shifts too. New slang grows out of unique risks and routines. Going down means going to Earth, dropping into high gravity. Outside means stepping into a suit and into vacuum. Night and day are more about lighting schedules than about the sun. Safety rituals, checking suit seals, verifying airlock status, confirming dosimeter readings, become as automatic as looking both ways before crossing a street on Earth. Accents and norms drift. You have people who grew up hearing a mix of Earth languages over delayed calls, but speaking in tight, technical, safety-driven context with their local peers. Humour bends around confined spaces, high stakes and constant monitoring. You can see the separation forming not as hostility, but as a different baseline of what normal feels like. That cultural shift doesn't happen in a legal vacuum. You still have to decide who owns what, who is responsible when something breaks, and which laws actually apply 400,000 kilometers away from any national border. At the start, lunar bases operate under the laws of their sponsoring nations or consortia, and under the Outer Space Treaty, which says no country can claim sovereignty over the moon. That sounds clear in theory, but practice gets messy fast. You build tunnels and reactors with joint funding. You mine ice that multiple entities want. You have people from different countries living in the same habitat but working for different companies. So you start writing local rules, base charters, safety codes, and resource allocation frameworks that apply inside the settlement, no matter which flag is on your passport. Over 100 years, these grow into semi-independent governance systems. You have elected or appointed councils. You have safety regulators with real enforcement power. You have courts or arbitration panels handling disputes about water rights, energy quotas, land use inside lava tubes, even inheritance of industrial assets. Lawyers and economists on Earth argue about property rights in lunar land and ice. But on the moon, those questions are connected to real mortgages, contracts, and corporate balance sheets. You can't keep it theoretical when a family's home or a company's mine depends on the answer. All of this is happening in a place that is, by design, closed and high pressure, not just physically but psychologically. What does that do to mental health over decades when the whole town lives in a glorified bunker? Any high-risk, isolated environment, submarines, polar stations, remote oil rigs, shows higher levels of stress, depression, anxiety, and interpersonal conflict. A moon base is like that, but permanent, and filled not just with adults on rotation, but families, teenagers, and eventually elderly residents. So the base becomes a full-scale human factors experiment. You collect long-term data on mood, sleep cycles, conflict rates, and social patterns. You track how people respond to different lighting schedules, work rotations, recreation options, and layouts. Architecture changes in response. Early habitats are tight, purely functional, lots of narrow corridors and cramped rooms. Later designs carve out open internal plazas, long atrium-like tunnels where people can see more than 3 meters in front of their face. Simulated day-night lighting cycles run across ceilings and walls, giving people stronger time cues. Biophilic design, adding plants and water features, moves from nice to have to strongly recommended. You put green walls, small ponds, and even artificial streams inside some modules, not because you need them for life support, but because they reduce stress indicators in residents. Play spaces for kids, exercise zones, and quiet corners for privacy are all threaded into the design, as much a part of safety as air compressors and fire doors. Telemedicine and in-person mental health care are built into routine life. Regular psych check-ins are normal, not a sign of weakness. After a few ugly incidents, maybe a breakdown in a critical crew member, a violent conflict in a cramped module, the culture shifts toward open handling of mental health, backed by policy, not just goodwill. Under all of that, identity is drifting. For someone born and raised on the moon, with grandparents who also lived there, Earth is not home, it's somewhere else, somewhere heavy. Ask a moon-born teenager in year 100, "Where are you from?" The answer is not the United States or China or Europe in most cases. It's a specific crater name, a station, a habitat ring. Their idea of home is a tunnel network under regolith, a specific farm level, a sports hall, a particular view from a pressure window in the safe zone. Earth is the place you see in high-resolution streams and in school history lessons, a bright, distant sphere in the sky when you do go to the surface. It's the place with crushing 1G where visitors need training and medical support. It's important, but it is down there, not here. That shift from humans as an earthbound species to humans with real multi-generation roots somewhere else is one of the deepest changes in our history. It changes everything, and it's happening in a settlement that is still sitting on a geologically active, impact-hit world. Because while society, law and culture are settling in for the long haul, the ground under the base is not perfectly quiet. The moon itself is still changing slowly, unpredictably, in ways that can damage or destroy what you've built if you misjudge them. So what does 100 years of tiny impacts, moonquakes and shifting regolith actually do to the surface the base is sitting on? The lunar surface is constantly getting hit. Most of the impacts are tiny, sand-grain scale, but they still matter. Bigger ones, from fist-sized rocks up to boulders, are rarer but not zero even on human timescales. High-resolution images from orbit around the Moon and Mars already show new craters forming over just a few years. Over a full century around your base, you will see small fresh craters appear in your wider area, sometimes right next to roads, sometimes on top of berms, maybe even clipping an unshielded line or a small outbuilding. You treat that as a design fact, not a surprise. Critical cables do not run in a single straight trench. They are routed in separated channels with physical spacing and armoured segments, so that one unlucky impact does not cut power or data to an entire sector. Exposed tanks gets a sacrificial armour, blocks of regolith or printed shielding that can take a hit and be replaced, while the core tank behind stays intact. You keep critical nodes like main reactors and life support cores away from obvious high-risk zones. No building right at the base of a crater wall that could shed debris, no placing key hubs in spots that models show as statistically more likely to take larger impacts. You accept that some outer structures will eventually get punched, and you build them to be cheap, redundant and easy to replace. That is the impact side. But the moon isn't only getting bombarded from above, it is also creaking from the inside. How big a problem is it when the ground under you literally moves? The moon is not totally dead tectonically. It has shallow moonquakes, some up to around magnitude 5 on the same scale we use for earthquakes. These are driven by tidal forces from Earth and by the moon's own slow cooling and shrinking. Most of the time they are minor, but a magnitude 5 can be serious if you've built badly. By year 100, you have a dense network of seismometers both around your base and all over the moon, left behind by earlier missions and deployed by robots. You've recorded decades of data. You know which regions get more frequent quakes, how strong they get, and which directions the main stresses run. Habitat foundations are designed with that in mind. You do not rigidly bolt everything to bedrock and hope for the best. You use flexible couplings where tunnels meet, so modules can move a little without cracking. You install tuned mass dampers in tall internal structures, big weights on springs that counteract shaking. You avoid putting heavy infrastructure on slopes that might slump or slide under shaking, favouring flat, stable terrain whenever possible. That cuts the risk of a quake turning into a structural disaster. You might still see local damage, a cracked wall panel, a misaligned door, but not full collapse. The base learns to ride out quakes like buildings in modern seismic zones on Earth. Even between quakes, the ground isn't truly static. The near-surface regolith is constantly breathing with temperature. What does that slow, tiny motion do over decades? Each lunar day-night cycle, the upper soil layer heats and cools, expanding and contracting. Grains shift slightly, microvoids open and close. Over decades, that adds up to slow thermal creep. Small pits fill in, sharp edges soften. On slopes, this leads to very slow, dry, granular flow, kind of ultra-slow landslide. If you put a cable, a pipe, or a small foundation on a gentle slope and leave it for 30, 50, 100 years, the regolith can gradually move under it. Footings can be undercut, exposing supports. Trenches can fill in, burying access routes or junction boxes. A road that was level in year 10 might have subtle ridges and dips in year 60 that stress vehicles and rails. Engineers learn to classify slopes. Some angles and soil types are stable essentially forever. Others creep measurably on decade timescales. You end up with maps that say, build here and you're fine for centuries, and build here and you'll be constantly digging things out. All of that affects where you place one of your most valuable resources, the ice in permanently shadowed craters, and how hard you dare to mine it. How do you pull ice out for 100 years without wrecking the very deposits you rely on? Permanently shadowed regions at the poles sit below roughly minus 150 degrees Celsius, minus 238 Fahrenheit. At those temperatures, ice mixed into the soil can stay stable for millions of years if you leave it alone. But you don't leave it alone. Mining brings in lights, heating from equipment, trucks or conveyor systems, and constant excavation. That changes the thermal environment. Sunlight reflecting from hardware, or waste heat leaking out, can warm surfaces that were once locked in deep freeze. Over a century, that can cause ice to sublimate, to turn straight from solid to vapor and escape if you're careless. So you monitor everything. You bury thermal sensors and watch how temperatures change at different depths as you dig. You measure how fast local ice content drops in active pits, and how it behaves in untouched control zones. You learn whether there is any significant recharge, ice slowly diffusing up from deeper layers, or whether what you see near the surface is basically a finite fossil deposit. If it's finite, you have to plan extraction rates over centuries, not just years, or you'll burn through your local supply and face a hard limit that industry and life support cannot easily cross. That leads to another uncomfortable question. On a world with no trees, no animals, no classic environment, what does environmental protection even mean? Are you free to chew up any crater you want, or are there things on the moon you treat as off-limits? As you dig, blast and build, you erase pristine scientific records. The upper regolith holds a layered history of impacts, solar wind implantation, and maybe even rare particles from distant cosmic events. The extremely thin lunar exosphere and delicate phenomena, like electrostatically levitated dust, can be easily disrupted by big human operations. If you cover a region with dust from repeated landings, build reactors and radiators, and run mass drivers over it, you permanently change that local environment. For science, that can mean losing a unique archive of billions of years. By year 100, the base is big enough that these choices can't be ignored. You set aside science preserves, zones where mining and heavy construction are banned or strictly limited. You define protected areas for specific phenomena, a crater used as a long-term impact record, a region used for exosphere studies. You write rules for how much dust you're allowed to pump into a region with rocket exhaust, or how bright and hot your lighting can be in formerly dark craters. The tension is clear. You are building an industrial hub on a world that also holds irreplaceable data about the early solar system and the space environment. There is no forest to save, no animals to rescue, but there is information you cannot get back once it's disturbed. Ethics shift from protect life to protect knowledge, and you're making those calls in real time, not in theory. While all this is happening on and under the surface, something else is filling up the space above the moon. Not just a few probes and one or two stations, but a whole traffic network of satellites, tugs, depots and ferries moving constantly between Earth and Moon. So after 100 years, what does the Earth-Moon system itself look like, when cislunar space is crowded enough that you need real traffic control and the Moon is just one node in a much larger web? Light takes about 1.3 seconds to go one way between Earth and Moon, so about 2.6 seconds for a full round trip. That sounds small, but it's just enough to ruin the idea of real-time joysticking from Earth. If you try to manually fly a lander or operate a drill from the ground with that delay, you overshoot, correct too late, and fight lag the whole time. So from very early on, the moon base is built around local autonomy. Robots drive themselves, local AI handles routine decisions, and humans on the moon make time-critical calls. Earth sends high-level goals, not real-time steering commands. While latency stays fixed, bandwidth does not. Over 100 years, capacity between Earth and Moon jumps from early kilobits and low megabits per second to terabits per second. You get this with high-power laser links between relay satellites and optical ground stations, backed up by radio for bad weather on Earth's side. Redundant constellations make sure you always have line of sight to something. By year 100, the Moon is effectively always online. Continuous high-res video, massive science data sets, live industrial telemetry, personal calls, entertainment streams, all flow both ways as easily as transoceanic fibre on Earth. The only reminder that you're 400,000 kilometers away is that slight pause before someone on the other end laughs at your joke. Once you have that kind of connectivity, you stop guessing where things are and start tracking everything precisely. How do you know where every rover, lander and satellite is in a volume of space that big all the time? You build a lunar positioning system, the Moon's version of GPS. A constellation of satellites in cislunar space and in various lunar orbits broadcasts ultra-precise timing signals. Receivers on the surface, in orbit and in transit measure those signals and compute their positions down to centimeters. Surface vehicles, drones, bulldozers and drill rigs navigate with this. A regolith hauler can follow the same narrow path thousands of times, minimizing dust disturbance. Autonomous drills can sink shafts within a meter of a planned target from kilometers away. Landers use it as an additional reference layer on top of optical navigation to nail their touchdown points on crowded pads. The long-term tracking also refines our understanding of the Moon's motion. Decades of precise orbit and rotation data feed straight back into Earth science. You get better models of Earth's tides, core dynamics, and even long-term climate signals, because the Earth-Moon system is coupled. So a navigation tool for mining and traffic ends up improving geophysics on the home planet. With accurate positions and tons of hardware moving around, you hit the next hard problem, not just where is everything, but how do we keep everything from crashing into everything else? Cislunar space fills up. You have communication relays, weather and Earth observation satellites that now use lunar orbits, transfer stages moving cargo, propellant depots parked at useful points, failed spacecraft, and stray debris. Orbits cross. Relative speeds are several kilometers per second. A collision at that speed is a high-energy explosion, not a fender bender. So you build space traffic control not as a one-off center, but as a set of coordinated services. Tracking radars, optical telescopes and onboard transponders feed position data into shared catalogues. Routes between standard waypoints are formalized into lanes, just like shipping lanes or airways on Earth. You set up standard approach corridors for stations and depots and low-traffic quiet zones reserved for sensitive instruments. Conjunction analysis, checking for close passes, becomes routine. When the system flags a possible near-miss, vehicles perform small avoidance burns, scheduled well in advance when possible, or quickly if something unexpected shows up. Dedicated cleanup missions grab dead satellites and large debris pieces, either deorbiting them into controlled impacts on the Moon, or parking them in graveyard orbits. All this discipline is not just about safety, it's also about money. Because by year 100, cislunar space is not a cool science zone, it's a real economic region. How does the difference between Earth's deep gravity well and the Moon's shallow one twist the way trade works? Earth's escape velocity is about 11.2 kilometers per second. The Moon's is around 2.38 kilometers per second. That difference decides where it makes sense to put heavy industry. Anything that needs a lot of mass, metals, bulk structures, propellant, is cheaper to do on the Moon or in cislunar space once you've built the initial factories, because getting that mass up from Earth costs so much more energy and money. So heavy industry migrates outward. You refine metals on the moon. You build large frames, tanks, and radiation shields in lunar orbit. You produce propellant at the poles. Earth stays the hub for high-value, low-mass things, biotech products, microelectronics design, software, culture, financial services. Data, designs, and small, very high-value components flow outward. Bulk commodities and large hardware flow inward from the moon. By year 100, people talk about cislunar GDP without irony. Government budgets, corporate reports, and economic forecasts treat the Earth-Moon region as a connected economic zone. Insurance markets price risk for lunar mining just like they do for offshore drilling. Currencies and contracts exist specifically for trade between orbital depots, lunar bases, and Earth nations. That economic flow also drives information flow. What does culture look like when the moon is plugged into Earth's internet, with just enough delay to be noticeable, but not enough to cut the cord? Streaming from the moon is normal. You watch live feeds of sports played in 1/6G, with players jumping higher and moving differently than any Earth league. You follow low-G performing arts, dance and stunts that would be physically impossible under 1G. You see long-form science collaborations where Earth-based labs and lunar labs run synchronized experiments and release joint results. At the same time, lunar residents watch Earth media. Earth fashion trends show up in low-gravity adapted clothing designs. But that 2.6-second round-trip delay is always there, just enough to remind everyone on both ends that this is not the same world, that conversations don't quite feel like being in the same room. Information is two-way, but experiences diverge. That feedback loop shapes identity on both sides. Earth populations start to see the moon not as a distant dream, but as another region, with its own news, dramas, and celebrities. Lunar populations feel the pull of Earth culture, but also push back with their own norms and priorities, heavily influenced by safety, resource limits, and high-risk tech everywhere. And under all that traffic and trade, a bigger shift is brewing. Once you've turned the Earth-Moon system into a working, economically active network, the step from there to the rest of the solar system is much smaller. So after cislunar space becomes routine, what happens to exploration and settlement beyond, when the moon isn't the end of the road anymore, but just the first junction on a much larger map? The biggest shift is where you launch serious missions from. Early interplanetary missions leave directly from Earth, riding huge rockets that have to claw their way out of Earth's deep gravity well. Once you have propellant and hardware coming from the moon, that changes. Earth's escape speed is about 11.2 kilometers per second. The moon's is about 2.38 kilometers per second. That gap is enormous in engineering terms. After 100 years, standard practice for big missions is simple. You assemble and fuel them in cislunar space, not on a launch pad by the ocean. Heavy components for Mars ships, asteroid tugs, even probes for the outer planets, are built on the moon or in lunar orbit factories. They are launched into space by mass drivers or small tugs, then docked together at depots or assembly yards near the Earth-Moon Lagrange points. Propellant tanks are filled from lunar-sourced hydrogen and oxygen. From there, departure burns for Mars or the asteroid belt are much cheaper in terms of fuel mass than launching those same vehicles wet from Earth. You still launch people and some delicate equipment from Earth, but the giant structures and most of the fuel come from the moon. In that sense, the moon turns into the Cape Canaveral of the solar system, but with lighter rockets leaving Earth and heavier infrastructure out in space. As soon as that pipeline is stable, people look at the next obvious resource targets, asteroids. How much easier does that step get once you already know how to live off rock and vacuum? By year 100, your engineers have a century of hands-on experience with regolith handling, vacuum metallurgy, in situ resource utilization, and closed life support. You already know how to run autonomous excavators, how to control dust, how to keep people alive in metal caves. Almost everything you learned on the moon ports straight over to asteroids. Water-rich near-Earth asteroids become high-priority targets. You send robotic and crewed missions from cislunar space using lunar propellant. Those missions mine ice and send volatiles back as water, or as cryogenic hydrogen and oxygen. Other asteroids, rich in metals like nickel and platinum group of elements, supply raw materials that are rare or hard to extract on Earth. Over time, a new flow of resources appears, not just Moon to Earth, but asteroid to cislunar space. Propellant from certain asteroids might top up depots. Exotic metals from others feed factories in full orbit that build high-end component or massive structures. The economic centre of mass for some industries starts drifting outward, away from Earth's surface, into the Earth-Moon asteroid network. That raises a deeper point. For most of history, we defined habitable as a planet with air, liquid water, and the right temperature. The Moon breaks that definition. It has none of those things, yet you still have a stable community there after a century. What does that do to the way we classify worlds? The Moon sits well outside the classic idea of a stellar habitable zone on its own. No atmosphere, no seas, brutal temperature swings, intense radiation. But with infrastructure, thick regolith roofs, reactors, closed ecosystem, transport links, it supports multi-generation human life here. That forces a rewrite. Habitability stops being only a planetary property and becomes an infrastructural one. A rocky moon without air becomes habitable if you can surround yourself with the right systems and keep them running. Suddenly, other bodies that were written off as dead rocks, like Phobos, Deimos, many main belt asteroids, small moons around Jupiter and Saturn, become potential sites for engineered habitats. Astronomers still care about natural habitable zones for native life, but for humans, the question shifts from, does this world have air and water, to how hard is it to build and power what we need here? The Moon base is the proof of concept for that thinking. Once you accept that, you have to look up and ask the uncomfortable question again, the Fermi paradox. If we can do all this in a single century of focused effort, in one star system, where is everyone else? The Moon base doesn't answer the paradox, but it gives one hard data point. One civilization, around one ordinary star, using 21st to 22nd century technology, can turn a sterile satellite into a functioning, partly self-sufficient world city in about 100 years. That changes the math in a lot of arguments. Any model of galactic civilizations now has to allow for the fact that turning dead rocks into networked habitats is feasible on very short cosmic timescales. The bottlenecks, the great filters, must be somewhere else. Maybe in the origin of life, in intelligence, in social stability, or in managing high-risk tech without wiping yourself out. Your Moon base becomes part of that discussion. It shows that at least one species can get off its cradle and spread to a place that was absolutely uninhabitable in its natural state. If we can do that this fast, the silence out there looks stranger. And that brings you to the technologies that made all of this possible and the risks they carry. Automation, AMI, biotech, advanced materials, and on the Moon, these aren't optional extras, they're mandatory. How does running them under such tight constraints change the way you handle them on Earth? In a closed habitat, a software bug that takes down life support routing is more than an outage, it's a direct safety threat. An AI that optimizes the wrong metric could starve part of the base of air or power. A biocontainment failure in a life support bioreactor could poison an entire air or water loop. There is very little slack. So over 100 years, the Moon becomes a stress test environment for high-risk tech. Every serious system has to go through harsh verification and redundancy. AI control loops are constrained by hard physical limits and fail-safes. Critical software is developed under stricter standards than civilian code on Earth, with formal verification and multiple independent implementations. Biotech is run in layers of containment, with genetic kill switches, multi-stage filters, and constant monitoring. When something does go wrong, and over a century you will have incidents, the investigations are intense. You trace root causes, you update protocols, and those updates don't stay on the Moon. They feed back into Earth regulations for AI, for synthetic biology, for autonomous industry. In that way, the Moon is both a test bed and an early warning system. It shows what happens when cutting-edge technology is not a luxury but the only thing between a thriving city and a disaster in vacuum. The lessons you learn there shape how humanity manages similar risks down on Earth and in the expanding web of habitats elsewhere. All of that raises a final question. 100 years in, this base is no longer just an experiment. It's a place, with history, with industry, with children and graves. What happens over the next 100? Does it die, boom into a megacity, or turn into something culturally separate from Earth? One path is simple and brutal, you just walk away. Funding drops, new priorities appear, and industry finds better options. Maybe asteroid mining gets so efficient that lunar ice and metals are no longer the cheapest choice. Maybe support on Earth swings hard to other projects. Bit by bit, the base stops growing, then stops upgrading, then starts shutting pieces down. First you halt expansion. New tunnels are postponed, then cancelled. Then you retire older modules without replacing them. The staff count drops from thousands to hundreds, then to a caretaker crew. At some point, the cost of even that crew becomes hard to justify when most activity has shifted elsewhere in the solar system. So you plan a controlled stop. You move people out in waves. You drain and store remaining propellant. You offload anything easily reusable to stations in cislunar space. You shut down reactors and entomb their cores. You seal hatches, equalize some modules with vacuum to reduce stress on old hulls, and leave a skeleton network of low-power systems, a few reactors or RTGs, some thermal control, basic telemetry. Then you go dark. A century later, a new expedition comes back with fresh ships and better suits. They walk through preserved, airless shells under the regolith. Plastics are brittle, colours are faded, but metals and ceramics are almost unchanged, because vacuum and dry cold are kind to chemistry. It's a lunar Pompeii of early spaceflight, frozen in place, frozen in time. From a distance, the base looks like a historic artifact. Up close, every panel and hatch is a reminder of what it took just to make Year 1 possible. But that's only one endgame. There's another, where instead of fading out, everything locks in and compounds. What happens if the base never slows down? If industry, science, and population all kick into a feedback loop? In that scenario, those first few tunnels are just the seed. Ore production climbs, propellant exports rise, more missions stage from cislunar yards, more labs and companies want direct access. The base adds modules, then whole new nodes. You go from hundreds of residents to thousands, then to tens of thousands over the next century. Multiple settlements appear around the poles and in other favourable regions, each with its own focus, one heavy on mining, another on science, another on manufacturing and data. You link them with maglev lines and buried transit tunnels, so crossing 100 kilometres at 300 to 500 kilometres per hour, a couple hundred to a few hundred miles per hour, becomes a standard commute for freight and even for people. You then tap into lava tubes, huge natural tunnels formed by ancient volcanic flows. Some of these may be tens of kilometres long and hundreds of metres wide, like enclosed valleys. You line them with regolith-based structures, pressurise them, and build neighbourhoods, farms and recreation spaces inside. These become whole valley habitats, where you can see hundreds of metres in both directions without running into a pressure bulkhead. The moon in this mode becomes a specialised urban world. Half factory, refineries, printers, reactors, mass drivers. Half data centre and logistics hub and servers and cold tunnels, control centres, docking yards. Human neighbourhoods are tucked under metres of rock, attached to that industrial spine. It's not pretty by Earth City standards, but it's dense, specialised and vital. At that scale, another pressure starts to build. How long do you stay an outpost when most of the people there have never lived on Earth? At some point, you cross classic colonial thresholds. Moonborn residents outnumber Earthborn. The local economy is mostly self-sufficient for basics, air, water, food, power, and a lot of hardware, and deeply plugged into cislunar trade. The people making decisions on Earth might have never visited the moon, and their rules start to feel disconnected from on-the-ground reality in 1/6 G. Local councils and charters gradually claim more authority. Maybe at first they handle only internal safety codes and resource allocation. Then they push for control over immigration, local taxes, industrial policy, and external contracts. Earth governments and corporations resist at first because they've put in the initial capital and still see the moon as an asset, not a partner. You don't necessarily get a violent revolution, but you do get movements that demand formal recognition, representation, and eventually self-governance. Legal frameworks, maybe new treaties, are forced to catch up. Either you negotiate a clear status, something like a federation member, a self-governing territory, or a new category entirely, or you risk open crises. Strikes, refusals to follow directives from Earth, maybe even control disputes over key infrastructure like reactors and the mass drivers. The question becomes a test case for all future off-Earth settlements. Can humans negotiate sovereignty in space without war? Or do we repeat the same colonial conflicts we had on Earth, just 400,000 kilometers away? All of that is happening while technology keeps evolving. There's also the possibility that without any drama, the original base just gets overtaken by newer, better ideas. What if halfway through this 100-year span, you get breakthroughs that make the first-generation moon base look ancient? Say cheap, reliable fusion finally works. Or ultra-efficient propulsion turns some asteroids into better industrial hubs than the moon. Or we start building enormous free-flying habitats, O'Neill cylinder-style megastations, that offer full 1G, Earth-like lighting cycles, and arbitrarily large rotating land areas. Compared to that, a buried 1/6 G city under regolith feels like a cramped, high-risk mining town. New investment might go into those orbital mega-habitats or deep space nodes. The original lunar base risks sliding into the background, not abandoned, but no longer cutting edge. In that case, the moon shifts into the role old ports and industrial towns play on Earth. Its power systems, life support, and factories look crude next to newer hubs, but the place keeps value. It is a historical centre, with museums and preserved facilities. It is a logistics waypoint, still perfectly placed for certain routes. It is a proven, resilient fallback location with known geology and known hazards, which counts for a lot when some shiny new project out in the belt has a bad decade. So you have these branches: abandonment, megacity, technological overshadowing. Under all of them, one change is the same, and it doesn't depend on which path you take. After 100 years of continuous presence, the biggest shift is in our head. The old baseline, humans belong on Earth, is broken permanently. Once you've had multiple generations grow up, work and raise families on the moon, the word space stops meaning a scary, distant vacuum you visit in rockets. It just becomes everywhere that isn't inside an atmosphere. The moon is an address, not an expedition. It sits next to Mars bases, asteroid habitats and orbital stations on a growing mental map of places where people live. Cosmology at the human scale changes. The universe stops being just a backdrop you look at through telescopes and becomes terrain. The same way ancient people once thought in terms of their valley, then later of continents and the whole globe, future people think in terms of planetary systems, and then of networks of engineered worlds. And the seed of that shift, the first clear proof that it's not just talk, is a moon base that hits year 100, still standing, still pressurized, with walls scarred by micrometeoroids, systems rebuilt 10 times over, and a population that no longer thinks of itself as visiting. At that point, the question is not will we stay in space, it's what do we turn into next, now that we know we don't actually have to live on planets at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.